Welcome everybody. This lesson we're going to talk about vectors in the linear algebra part, and as promised in languages we're going to look at a way of using graphs to look at a regular language. So let's start with the linear algebra part. So what is a vector? A vector is very simply a matrix with only one column. And a vector has something to do about movement in space. If we have a vector of only two letters, so the first one, which is 4, 1, then this means that we have a movement in a two-dimensional space. So for instance, this 4 we look at as going 4 steps to the right, so 1, 2, 3, 4, and 1 step up. So the vector would be the connection, and then in a straight line, of course, the connection from the starting point to the end point. If we have a vector in the three-dimensional space, it means for this example, we go 1 to the right in the x direction, 3 in the y direction, and 4 in the z direction. As you see how badly I can draw straight lines, I will not risk of doing that in a three-dimensional space. So a vector is just an arrow, a movement in 2 dimensions or 3 dimensions. So the one we gave you, 4, 1, go 4 to the right, 1 up. And an arrow has a length and a direction. It doesn't have a starting point, so you can start this vector anywhere in space. It doesn't have to be from the origin, but it can start at any point on your grid. If we look at the difference between vectors and points, then a point is really some point in space. So if I have a two-dimension and this is point 0, 0, then the point 2, 1 would exactly be this position, 2 to the right, 1 up. So this is a point, and we denote this point with a capital letter. So for instance, this point could be F with 2, 1. If we look at a vector with the same numbers, so 2 to the right, 1 up, then we could have this vector start anywhere in space. For instance here, 2 to the right, 1 up, and we have this vector. So this vector doesn't have to start in the origin. That's a big difference. And a vector we always denote with a smaller letter. So this vector could be a vector F. We can use vectors in operations, and a very simple one, we can add two vectors. So, for instance, if we would take the vector A being 1 minus 2, and a vector B being 0, 3, then we could have these vectors added. So let's just start somewhere in space and draw vector A. So it goes 1 to the right, 2 to the left, 2 to the bottom. So this is vector A. Vector B has 0 to the right and 3 up. So if we add those two vectors, we should start from the ending point of vector A. So that means we go 3 up. The total vector, so the sum A plus B, would be this one. So starting from A, continuing at the end point of A with B, and then the result would be from the starting point of A to the end point of B. And this vector is then the result of A and B. We could also subtract two vectors, and in fact that's basically the same thing as adding vectors. So let's do the same vectors as we just did now. So we have A being 1 minus 2. We have B being 0, 3. And if we now subtract the vectors, so again, we start from A at some point. So 1 to the right, 2 to the bottom. So this is the vector A. We subtract 0, 3, so that means that we have, in fact, an adding of vector minus b. So that would be 0 minus 3, and that means we don't go up, but we go down 3 spots. So this is vector b. Okay, so the total result would be from the starting point to the end point. So this one would be a minus b. We can also just have a scalar multiplication, and that could be positive or negative. So if we look at vector a being 1 minus 2, so let's start somewhere, go 1 to the right, 2 to the bottom. So this is the vector. Then we could multiply, for instance, with 2. And then it just means that the size of the vector will become 2 more than the original one. So this total thing here is 2a. If we would have a negative multiplication, so for instance minus 1, then we would start at this position and then go exactly in the opposite direction. So this one would be minus 1, minus a. If we have 2 points, for instance a being 3, 1 and b being 5, minus 2, then we can find a vector from a to b. So how does this work? So we have 2 points, so that means we have to really position them in space. Point A being 3 to the right, 1 up, so this would be A. And we have point B, 5 to the right, 2 down, so about here we have B. Then we can have a vector from A to B. And if we want to calculate this exact vector, it's just a matter of looking at the movement in both directions. So how can we get from A to B if we look at the movement in the x direction? Okay, so this is the x-axis, this is the y-axis. So how can we move from A to B in the x direction? So we have to go from 3 to 5. So that means we have to move 2 to the right. If we look at the y direction, we have to go from 1 to minus 2. So that means we have to go 3 down. So the total vector would be 2 minus 3. We have a line in 2 dimensions already seen in the previous lessons as represented by a linear equation. For example, 3x plus 4y equals 12. We can also have a new way of looking at this line, and that's with the help of a vector form. So with this vector form, we have all x, y's on the line depicted with a starting point, some point on the line, and a direction vector. And if we have, for instance, so if we have, for instance, if we look at an x and a y, we have a plane. For instance, we have a point AB, which is so for instance, if we look at a point, let's say we call this point here A, and I have a vector like this one. The combination of the two will give us a line. So I have a starting point, which is this one, and then I can have a scalar multiplication of this vector, which will give me the complete line. If I have a negative multiplication, I go to the left. If I have a positive multiplication, I go to the right. So this complete line is given with the help of one point and one vector. This vector is called the direction vector. And the lambda we are using is the scalar multiplication. So this can be anything from minus infinite to positive infinite, is called the parameter. So how do I get from a linear equation to a vector form? Well, basically that's quite simple. So if we have a linear equation, we already know how to draw the graph, how to draw the line. So then if we have the line, let's say this is the line, we just find 2 points on the line. So for instance, point A, point B. So then one of the points can be used as the starting point. And with the help of the other point, we can calculate the direction vector. So A, B. So in that direction. And then together, so xy would be the starting point, this point A, plus lambda, the parameter, times the direction vector AB. So let's see how this goes. So let's say we have a line 2, 1, and 4 to the points 2, 1 and 4, 2. So let me try to make this. So I have a point 2, 1, so this one, and I have a point 4, 2. So this one. Then the line which goes to these points is the line given with the help of those two elements. So now we have two ways of making this line visible in a mathematical notation. We can do the vector form notation, or we can do the equation. Let's start with the vector form. So for the vector form, we need 1 point on the line. So let's choose this one. So point 2, 1. So xy would be some starting point, and we chose 2, 1, plus a parameter, lambda, times the direction vector. So we need to have a movement on this line. So let's just go from this point to that point. So that means in the x direction I have to go from 2 to 4. So that means a movement to the right of 2. And for the other direction, in the y direction, I have to go from 1 to 2. So that would be a movement of 1. So the vector form for this line is given with xy being 2, 1 plus lambda times 2, 1. And maybe you see something funny. This 2, 1 here are identical. Well, that only means in this situation that the xy, this line, also has a point going through the origin. This one here. So we could just as well have written this one as xy being 0, 0 plus lambda 2, 1. And even simpler, we could just omit the 0, 0 and just write this line as xy being lambda times 2, 1.